I decided to put in some slides in the presentation of this morning to show something that I only mentioned without really showing it. So this slide is from a paper, relatively old paper, 1981 by Jeff Watch, which shows like a typical model of eruption rate during effusive eruptions, which shows this waxing flow and then waning flow, like first increasing and then decreasing, with nearly exponential rate after the maximum and then increase there. So for the initial phase, people agree that it must be some sort of conduit diameter change, and this is starting to be included in this kind of models, while I want to show you now that actually the exponentially decreasing thing, I mentioned you a model for that, like the pressure, the magma chamber loses pressure. Yes, this is a general thing, but actually there are kind of 3 ways in which this can happen. So I wanted to go through these 3 ways because it's good to keep it in mind, and all 3 generate an exponentially decreasing rate, but with different time scale. So like in one case, which is maybe the most complicated, the other 2 are easier, there is a relaxation. It's blinking. Yeah. So in the first case, we have slides. So one case is we have the volcano, we have the magma chamber, and the magma chamber creates a dike, and the dike erupts. So, but the eruption occurs really fast. So actually we don't really see this trend. We only see the eruption. So basically then the conduit is created, the conduit is then enlarged, and then you have the eruption draining the chamber, and then you have basically so the pressure at the outlet remains the same all the time, remains the atmospheric pressure. And then you have the magma chamber losing pressure. So this is actually not the first one I show, but maybe the simplest. Then there is another one which is similar, but just what happens. So you have the volcano, and then the magma chamber, and then this results in a long dike that propagates. And then this is also draining the chamber, but you actually see the outflow rate at the chamber. So this is actually not really an effusion rate, it's more an outflow rate from the chamber. The other kind is an effusion rate. Here you see the deflation, and you can figure out the outflow rate, and the outflow rate is draining the chamber, and basically is changing with time. But here the pressure at the dike is not always the same necessarily. It depends also at what height it travels, and it depends what are the conditions. Anyway, you are basically, the way you solve it is slightly different, because you have to put mass conservation. What comes out of the chamber goes into the dike, and then basically you have to find an equilibrium pressure that will be the final pressure. When the 2 are at the same pressure, then the flow will stop. While in this case the flow will stop when the pressure, basically the whole head will be compensated exactly at the atmospheric pressure, or if the flow will somehow be clogged by magma freezing. And then there is a third one, which is during caldera collapse. So in both cases, especially in this case, actually, when you drain the magma chamber, sometimes the drainage is very effective by, for example, a siphon effect, as we discussed on the very first days. And then the weight of the overlying rock is not sustained very well, and you can create a caldera collapse. And then you have actually here, so this drains, so you have this going away, and then you have this dropping. If you do this, so both the other two result in an exponentially decreasing flow rate. In this case too. Why? Because you have the column of magma, so basically the elasticity here is not the reason. Elasticity is gone because you are breaking the rock all the time. In the other case it was elasticity, and now we are going to look a little bit on how formally we can model that. While in this case elasticity is gone, you break it, and therefore there is no elastic relaxation of the magma chamber. It's more that you are basically decreasing, let's say, decreasing the height of this column above the magma. And therefore, it's like a spilling, you know, one of those hydraulic spilling things, by which the pressure here below is the pressure of the entire column of weight that is above it. And therefore, while this column drains, you have a decreasing pressure, and the decreasing pressure is proportional to the height of the column. And this also results in an exponentially decreasing rate. So you actually have, if you have effusive eruptions, it's more like the first and the second, while if you have also a measure of the outflow from the magma chamber from elastic deformation data, you can also consider the second one that I put here. But I wanted to discuss now the compressibility, because it's also important for the caldera collapse problem, actually, for different reasons. And in general, it's a very important point that is often neglected, so I think it's good to remember magma compressibility and elastic compressibility. So basically, we can say, like if you take those equations, the second one, you know, if I change the mass within a magma chamber in time, so I can imagine to put some mass or to extract some mass, is actually the same. What I'm actually doing, mass is like the product of density and volume, and actually what I'm doing, I'm changing both, because when I extract, let's say I put some mass in, then what I'm doing, I'm both squeezing the magma that is already in there, so I'm changing the density of the magma that is already in there, and also I'm changing the volume, I'm changing both. So actually, like there, you can write basically the derivative of, so you can express it in terms of pressure rather than in terms of time, and then you can say the derivative of the volume and the derivative of the density of the magma. And then you can define two constants, or actually constants in very first approximation, because they are not that constant actually. One is the compressibility of magma. Compressibility of magma is the relative density variation for a pressure change, and the compressibility of let's say elastic compressibility is a relative variation of volume for a pressure change. This one is actually the inverse of the bulk modulus, which is a more known parameter. So sometimes one speaks in terms of bulk modulus, sometimes of elasticity. The same is true for magma. In one case it's the bulk modulus of magma, in one case it's more the bulk modulus. Actually, it's better to write it here rather than here. This is really the inverse of the bulk modulus of magma, While here actually is not really the bulk modulus of rock, because it depends on the shape of the chamber. Why? Because shapes are not all the same. So if you take, let's say, a crack-shaped reservoir, already intuitively, a crack-shaped reservoir can be squeezed or enlarged with a tiny variation of pressure by some amount of volume, you know, because it's flat, and therefore you don't have to apply a lot of pressure to actually squeeze it more, and to extract or to inject. So it's easy to inject more mass into a crack rather than into a big ball that is spherical, for example. Indeed, you can see this by derivating the expression for the volume of a crack, volume change of a crack, because, well, I can write it down. Like if you have a crack, penny-shaped crack, so-called, the volume, I think, if I'm not entirely wrong, is something like this: 1 minus the Poisson's number over the rigidity, and then it's magma pressure minus the normal stress. So basically the pressure of the magma minus the normal stress is what creates an opening, and then of course you have some elastic constants, and then there is something missing, which is the radius of the crack to the third power. If you derive this by pressure, basically what you get, all the constants get kind of eliminated, and you have that the compressibility is just proportional to 1 over P minus sigma. And this basically tells you that the compressibility is very high, so you can compress it easily, because, or at least high in comparison to something spherical. Well, if you do the same with a spherical source, you obtain that this is actually really incompressible. You have to apply a lot of pressure into a sphere to just expand it by a bit. And this is because of the shape, just because of the shape. So, and then you have a lot of shapes, you know, but generally the compressibility is really related to the aspect ratio. So if you have a crack aspect ratio, then it's very compressible. If you have a sphere, it's the least compressible structure. And then if you have like something elongated like this, it's ellipsoid, but I always am confused between prolate and oblate. If it is elongated like this, then it is also very compressible, not as much as the sphere, but almost. Only cracks are very compressible. So, and then of course, but then of course it depends also on the rigidity or on the bulk modulus of the rock, how compressible it is. So compressibilities in case of spherical things, and considering the bulk modulus, are more like 10 to the minus 10 pascals. Yeah, to the minus 1, because it's an inverse of a pressure. The 10 to the minus 10 Pascal to the minus 1, the units, it's the inverse of a pressure. While overpressures in cracks are generally of the order of some megapascals, so they are then 10 to the minus 7 of the order Pascal to the minus 1. So they are much more compressible than the spherical thing, really orders of magnitude. Okay, what about the upper one? The upper one, magma compressibility, is a parameter. It strongly depends, as you can imagine, from the gas content. So if I take like a gas poor magma or gas-free magma, the compressibility is more similar to the sphere, actually 10 to the minus 10 or even 11 Pascal to the minus 1. If I take gas, this can increase a lot compressibility and get much more similar to the crack thing. So why is this important that they are similar? Because if you look at the expression here, this one, you see that they are summed into in these relations. They are often the summation of the two. Sometimes it's the ratio of the two. It depends on what process you consider. They end up being summed together, or they end up being divided one by the other. So if they are similar, then ratios can become like similar to 1. If they are very different, the ratios can become 0. If they are very similar, their summation is going to be, similar, of the same order, but if one of the two is really much larger, then the other one becomes insignificant. So you have actually some processes that may be very extreme because of this. So effect of magma compressibility can be seen in a lot of phenomena. For example, you see them when a magma chamber is drained into a dike, exactly. So if you have this, what happens is that the magma chamber will not change very much for the same pressure change, its volume, while the dike will be quite big for the same pressure change, because the compressibility is so different. Therefore, one can explain, as noticed by several people in the past, one can explain why the volumes of dikes are, well, now I don't have this slide, but maybe you remember, I don't know, when I showed you the crustal deformation of the upper dikes, or even of Mardarbunga, that there was a huge dike and the magma chambers were actually very small in comparison, even if we know that they provided the magma to the dike. The dike was a huge signal in the deformation, and the magma chamber resulted as just two tiny balls in the overall thing, to the extent that sometimes you don't even see the deflation if it's below, because it's smaller, it appears smaller in amplitude. The reason is exactly this, that the shapes very often of magma chamber is more, not necessarily spherical, but is more equidimensional. Maybe it's composed by a series of fractures that all merged into a spherical thing, or similar to spherical. Maybe by erosion they really get some volume that is kind of equidimensional. And then in this case you have that their volume loss is small and the dikes looks big. And if you make the ratios between reasonable parameters, you get something like 2 or 3 easily. So the dike can be 3 times as bigger than what the magma chamber has lost, which is a bit weird.
It's expanding.
Yeah, it's weird. However, so you can think of it like a balloon and gas tank problem. So you take a gas tank and you fill a balloon. You don't expect the balloon to actually gain the volume that the gas tank lost. You expect the balloon to gain much more volume. And the reasons are two. One is that the material is compressible, gas is compressible. Second reason is the material of the balloon is compressible, is elastic.
And the outside pressure is low for the balloon.
The outside pressure is low, but the tank doesn't really care. The balloon cares. So basically the balloon can elastically expand, and the gas can actually, so the gas tank doesn't lose so much volume because it's very rigid, very incompressible as a material, while the balloon is elastic. And the material, so if you would do that with water, if you did that with water, then you wouldn't see the same thing, because the gas tank could not lose the water. Water is incompressible. So actually you cannot even fill with a very rigid tank if it's a closed system, you know. You can only do if you actually empty the tank and you have some air in it. But if it was only water, you couldn't fill any balloon. The reason is that water is incompressible. So you need both compressibility of the material inside and compressibility of the source outside. If you don't have this, either you break the tank, create a caldera collapse, or you cannot do this. But they are compressible, and so this is an effect that you can see. There are many other effects. We talked in some classes before about the focal mechanisms, And actually I think that the compressibility is also very important there, because if you have compressibility, then you can have volume variations that due to a sudden pressure change, you can have a volume variation. If you don't have any compressibility, then you don't see any volume variation. And so I think this may be a reason why you see isotropic components sometimes, because you see a volume variation in the especially in crack-like structures. There are, I'm sure, a lot of other things that right now I don't recall, but it is a very important point, these compressibility things. Yes. Okay, this was also important, because what I want to do now is this magma caldera collapse equations. Here I have my notes. First of all, don't look so much at the notes, because it's more for me. We will do the equations. Okay, so consider a system that is really like a piston. This is like a rigid piston with mass m, and here we have a magma chamber with volume V0, and like assume that we are draining this chamber by an outflow rate called alpha, for example. Then we want to write the equations of motion for the piston. Okay, so the equation of motion for the piston moves vertically, so we have m z second derivative, like the acceleration for the vertical motion. And then, like if you look at the notes, we have like some factors there. I want now with you to figure out what these factors are. Okay, what are the forces that act to drive the piston down? And what are the forces that resist this motion? Okay, so you have help, because they are written there, up there in the equation, but it's written in Italian. So,
so I think the weight of the
weight of the
drag
piston.
it down, and there is a buoyant force due to the pressure of the volume of the chamber.
Okay, so the weight is actually this.
We have friction.
We have friction.
That act against.
Okay, we have friction on the walls, which is this F. It's the large F. Then we have two other factors, you see. One depends on alpha, if you see. And the other one depends on the actual displacement. Can we figure out what the two are, what the two factors are? So one is contrary to, so one, if you bring the one with Z to the other thing, you see that it plays a resisting role because it has the same sign as friction, while the other one is like a driving role because it has the opposite sign as friction. So the driving role with the drainage, maybe it's, so it's basically the suction. Why is that kappa, alpha? Okay, I tell you what the different terms are. So this small kappa is actually the magma bulk modulus, so it's, yeah, I'll write it. Magma bulk modulus. So basically we just wrote it before as magma compressibility. Then we have S is actually this surface. So it's the circle, the surface of the circle. So surface of caldera. And then we have V0 is the initial volume, and alpha is the outflow rate. We wrote that alpha, outflow rate, and V0 initial volume, and T is time. And T is time. Okay, so why is the suction cap? What has the compressibility to do with the suction force? So how do I arrive to write this term like that? So it's a force, okay? And so a force, in this case, I can write it as a pressure times a surface. So already I know why I have an S there. And then I have a pressure change due to the outflow rate. Okay, so basically I take some mass out. The outflow rate, alpha T, is basically, I can say that this is the mass change, or volume change actually. So basically I have delta V over V, and then kappa. And I can see that this is the pressure change. So before I had the pressure change, dP equal to 1 over this delta V over V. Yeah, it was written somehow differently, but it is the same thing. So I can do the same equal to kappa delta V over V. So actually, if I want to have the pressure change, the pressure drop due to an outflow rate, I can write it in this way. Like delta P equal to kappa delta V over V. And delta V is alpha times T. Okay, and then times S. So basically this last part is the pressure drop due to some magma exiting the chamber. But then what happens? It happens that the piston falls down, and I have some pressure gain due to the fact that the piston moves down. And this pressure gain again is kappa times delta V over V. And this time delta V over V is equal to Z, which is the displacement into the magma from the piston, times S, so times S, because Z times S is this delta V over V, and then kappa, and then I have another S because P is times S to get a force. So in this case I end up with 2S. Is this clear? I can repeat, it's no problem. Repeat? Okay, so let's write it. You know now what all these constants are. I keep this equation, and then I want to have basically the pressure. Pressure is like P0, like initial pressure, like some reference pressure, plus the delta P due to magma out, actually minus because pressure will decrease, and then plus delta P due to piston in. In one case I lose some pressure, in one case I gain some pressure. Okay, what is the pressure due to magma out? I use this equation, so it's going to be bulk modulus times delta V magma out over V0, which is kappa alpha T over V0. Yeah, this one is okay. The other one is piston in. So I have kappa times delta V piston in over V0. But this is kappa Z times S over V0. But then I have to take this pressure, multiply it by S to have a force to put it into the equation. And this is how I got to that equation there. Okay, then we need to solve the equation. we didn't do so much analytical things, but I think this problem is beautiful. And so I think it's the ideal one to actually do analytically. Okay, I have a differential equation. You can tell me what type of equation that is. Homogeneous, inhomogeneous, inhomogeneous, what order, second order, because it has a second derivative. Fine, then what? How do I solve an inhomogeneous equation? I first solve the homogeneous one. So I first go to the first part, so I write this. Actually, I put this and here. Okay, I define my frequency, typical frequency of my problem, and then the solution will be, you tell me, a combination of exponential, or actually in this case, yeah, exponentials is fine, always good. I can write in terms of exponential or sines and cosines. Okay, then I do this, and actually there are a few tricks that makes, so basically it will be sines and cosines. For example, A sine omega t plus B cosine omega t. And then I have initial conditions. So I make a derivative, which is like here, and I can put my initial condition will be that z at time 0 is 0, velocity as time 0 is 0, just to make it easier. This is fine. But it's not, so and this is relatively easy, and I can get my A and B in this way. Then I need a solution for the one particular solution for the inhomogeneous one to add to this general solution for the homogeneous one to get a final solution. But then there is another trick, and this is relatively easy. So this is basically the final solution. So first I add, this is a particular solution of the homogeneous one, inhomogeneous one, this one here, and this is the general solution. And then by applying my boundary conditions, I get my A and my B, and they are kind of here. Well, this is not difficult, it's actually easy. But the point is, now friction, because friction is tricky. When I do this, I need to be careful. And actually this took me, from the paper, took me a while to actually get this point, because it's not really explained very, very, very well. You need to consider your system and the assumption of a friction model. The easiest friction model is a static friction versus dynamic friction. Otherwise, you need to use a more complex friction, which is like rate state or whatever, right? Let's have the easiest friction model for now. So I need to wait that the drainage is far enough so that the force of suction overcomes the static friction. So this will tell me the time that it first takes for the dynamics to get an event, to get a slip event. And then the slip event will be described by this law, and then I see that it is actually some, the sines and cosines or exponential will basically describe a slip, and the time t will describe. So all this equation will describe the fact that the caldera will have a slip event that will finish And why it will finish? It will finish because it will slip and dip into this compressible magma that will actually resist and stop it. Okay? This is what these equations describe, like one motion of a piston. The time that it will take to actually move the piston first is the time needed. What is it? It's actually above here. Is this time here, because it's the time needed to actually for the outflow rate to really equate the frictional force. This will be the time before actually the slip starts. So you have a drainage and then you have this time. But then friction will immediately, once the event starts to slip, when the piston starts to slip, friction will collapse to dynamic friction. And then actually the motion will be driven by dynamic friction. So you have to substitute friction with the dynamic friction. But then what happens when the motion stops with a dynamic friction, friction will go back to static. But then the next time, to have a new event, you don't need to reach the static friction. You need to reach only the difference between static friction and dynamic friction. So actually it's a rather complicated thing, but in the end it's not that complicated. You just need to know how to deal with these friction things. And then what you get from this is actually a very weird dynamics, which is actually exactly the dynamics that is observed. And you have basically the piston will do something like this. Actually, it's not really like this, it's more like it will slip in individual events. And I can actually get from these equations the most important characteristics, which is one is this time here. I'll write it as a capital T. It is the time between individual events. Then I have another time scale, which is actually this one. It's much smaller than this. I write it as a tau. So this is the time scale of the actually slip event. So you have a time scale for the slip event. It's just generally earthquake-like. Maybe actually earthquake-like, maybe longer, maybe it's sometimes there's earthquakes, sometimes you have low frequency earthquakes, like very slow earthquakes, sometimes so slow that you don't even see it. So it's really cool because you can actually control the slip velocity by all these other parameters in a system. And then you can also get from the equations this, which is delta Z. So how much will the caldera slip every time? And the cool thing of all this model is that really, if you go to the individual volcanoes and you check, I'll open now a paper. We saw this slide actually, but I wanted to show you some better. So this is the time interval between two successive steps. Well, actually before I open, sorry for the confusion, before I open the paper by Kumagai, which is the paper who solved this particular solution, this one. Science paper. The observation actually here was really like the low frequency earthquakes. So these earthquakes were like, woo, you know, every collapse. And so he found an explanation and he modeled. So you will find basically it's the description, very, very meager description of all this that I showed you. So you need to concentrate to understand. And then there is an analytical expression for this tau quantity, which is actually the duration of an individual event, and it's all in terms of friction, pressure, surface of the caldera, you know, all these parameters. So you can actually put the parameters for your own caldera and see how quickly that will turn out to be. Then you have a delta Z, which is the overall slip. Again, it depends on the parameters, and then the time interval between two slip events, and again it depends on the parameters. So actually you can, so if we go back to the other paper, which basically describes, so this paper, by the way, the Kumagai solution for this was published after the Miyake-jima caldera collapse. After that there was one additional caldera collapse at Piton de la Fournaise. So the paper was published in 2001, I think. 2000 was the caldera collapse at Kilauea. At Miyake-jima, he did the solution, and then you remember it lasted, at Miyake-jima it lasted a few weeks. It was like 1 month and a half that the caldera collapse lasted. It was quite long, with the dike becoming fat and fat and fat. Then there was a caldera collapse at Piton de la Fournaise in 2007, and this lasted only 1 day and a half. So you see only 2 days here, Piton de la Fournaise. And the Miyake-jima is somewhere here. Where is it? Fernandina, Miyake-jima. This is weeks. So, and the Fernandina, which was a collapse that occurred in 1969, I think, at Fernandina, is also reported in this paper, and basically it looks entirely similar to Piton de la Fournaise, just on a different time scale. Here it's actually 1 week, and the model really describes all this. Like if you take the time interval, if you take the what is this? Downward displacement of the piston. You see the downward displacement of the piston also. So, okay, if you take the data and if you take this model, what can you see and what you can't see? So for the model solves the equation for everything constant. The initial volume in the chamber is not varied. The outflow rate is not varied. Everything is constant. So of course it can solve just one cycle. Yeah, because you are not varying the parameters of the model. The model is just steady state. Yeah. So actually, all these data are well described in terms of one cycle. So if you take just one of those points and the distance to the next point, this model really explains why you have all these steps, because those steps really occurred, many of them. Kilauea 2 last year, again the same. Initially they were super surprised, and you could see on Facebook, we observed this very strange step-like motion, and then people were answering, read your papers, because this had already been observed at many other volcanoes, and it's actually been explained by a model, so it's exactly how it's supposed to happen. Oh, okay, la la la. It was quite funny. Okay, but what can't you actually see? You see that now the downward displacement delta Z. Let's have a look at the formula for delta Z again. It's also reported in this paper. What is it? Okay, here is large T. The inter-event time, delta Z, where is it? Not given. Well, let's look in the Kumagai paper. Delta Z is here. It's actually written in a way that you don't see all the other parameters, because there is this K, but this K factor is actually, what is it?
Just in where?
Here, just below, huh? So actually, why, if you look at the data, okay, let's keep this open here, and let's keep this. why, so these are the individual piston events, piston movements. Tuck, 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 tuck. They become smaller and smaller and smaller. The first ones are big and the final ones are small. Delta Z is this, and one can see that actually it's more like, it depends on the initial volume, it depends on the caldera surface, it depends on friction and on compressibility. So actually what this paper does is it takes the steady state model and tries to argue why these parameters change over time, why the delta Z changes over time, why T changes over time, why tau changes over time.
In the same caldera or?
In the same caldera. In the same caldera, so actually why it changes from caldera to caldera is already explained by this, because you have to just put the parameters appropriate for, although this is not really very easy, because friction is like a very unknown parameter, and also the initial volume of the magma chamber is a bit of an unknown parameter. But if you do it, and you put, you can figure out what kind of parameters you need to put there, and they look reasonable, they look fine to actually get this. While for the same caldera, why it changes over time, this may be discussed because this model doesn't tell you. So either you solve the model for a varying friction, or a varying outflow rate, alpha, or a varying compressibility. So people discuss, debates why this is, and so some people are for what would you. I'm looking for a discussion. Very nice. Again, I'm looking for a discussion and not for the correct answer, just to discuss and get some ideas out. Why do you think it's very the concentrate? It's really impossible. Yeah, so let's look at Fernandina. It's actually beautiful. You see like a very smooth trend for these events. Okay, I'll ask you a lot of questions. So, do you think it's going to be, maybe if I can open another one where the laws are actually seen more clearly. What is it here? Here. Okay. I cannot really zoom a lot. Do you see it? Or is it too small? See? So basically you have that delta Z is basically proportional to friction, to volume in the magma chamber, and inverse of compressibility and inverse of surface of the caldera. Okay, surface area is tricky because we saw that there is an inner ring and an outer ring. But actually when this piston movement occurs, everything has already developed into vertical folds. Okay, because they basically what happens, first you have the inner ring, then you have the outer ring, but then you move it so much over time, like actually it's not the first collapse, it's actually something that occurred already 100 years ago, 200 years ago, so in the end you end up, this is seen also in analog experiments with sand, it's seen that in the end you end up having something that really slides on cylindrical walls. Okay, so friction, so we have a decreasing trend for Fernandina, for example, so it could be decreasing friction. Yes, it could. Because we know that when faults slip a lot, the friction actually on these faults it decreases. Could be. Then it could also be decreasing volume within the chamber, definitely, because we know that it decreases, right? It's definitely not increasing. Then it could also be increasing compressibility, increasing bulk modulus. Is this realistic that I have an increase in bulk modulus, that the material becomes more incompressible? I'm not sure, because you need to actually, what would
Because the degassing.
if you have degassing, will actually compressibility increase or decrease? So, okay, if you degas the magma,
Yeah,
okay, so you release gas
So it
from the
so it
magma.
increases.
Okay, well, you would need to have actually decrease of compressibility. But then, let's go to the inter-event time. If I have decreasing piston movements, you see that everything looks similar, except that I have also an outflow rate there. Everything else looks actually quite similar. I also miss an S. Yeah. So if I look now, so if I show you the piston movements, can you tell me more or less, given these equations, how the inter-event times will change?
The flow rate will decrease.
The flow rate will decrease. Therefore, flow rate will decrease, and it is at the denominator. Huh?
And the time period will become lower.
Yes, so, but we need to check whether actually it wins against the rest, because the rest is already describing a decrease. Yeah. So indeed it wins because if I go to the paper here, this was the outflow rate, the time interval between two subsequent eruptions. Actually, if you look at it, first of all, how do you measure it? How do you measure it? This is important because you can measure it in two ways. One way, which is better, is really having a GPS station on the caldera floor and seeing like the subsequent events. Another thing that you can do if you don't have this, which they did here in Fernandina because they didn't have any floor measurements, you can actually take the earthquakes, because if the slip events generate earthquakes, actually here it's time interval between two magnitude 4.4 or above. They are relatively large. I mean, they are measurable, and they are measurable quite well. You know, they are large events. At Bardarbunga, they were like magnitude 5, more or less, these caldera slips. So you can take the magnitude, you can take as events the time of these earthquakes, you know, and then it's a bit imprecise because sometimes you have some that are almost there, some that are much larger, so you don't actually know very well. It's actually better to have the geodesy measurements in the caldera floor, but it is better than nothing, right? So this is going to be my... Okay, one other random question. I'm shooting a lot of questions. What statistics will these earthquakes have? If I go and plot the magnitude frequency relation, what do I get?
The magnitude will...
Will I get yeah, a little bit, not so much in the end. It will do, but not so much. In the end, but if I plot, will I get a Gutenberg Richter, or will I get something different from a Gutenberg Richter? Why? It's correct. Why?
Because the magnitude...
Small earthquakes.
Because I have like all the time an earthquake with, so I will have also some smaller earthquakes because they are always there. But the nominating factor will be earthquakes that are relatively similar in magnitude and occurring at very similar times. You know, they change, but not so much.
like a characteristic earthquake.
It is like a characteristic earthquake, which is supposed not to exist, but actually here it is existing. So characteristic earthquakes, do you know what it is? Yeah, so it's basically if you take a very simple system, you pull it like a mass, you pull it, then it will slip in a characteristic earthquake fashion. In nature, they are really rare. Why are they really rare, and why do we have them here? I'm challenging you now. Why are they rare in nature?
This recurrence period will be larger.
Well, this is some people think it is like this because the return period is very large and we don't see them. But other people, they really object to this hypothesis and I say, no, it's not true. They really don't exist. The recurrence period is like a false
Myth.
It's a myth. And actually you don't have anything like that. Why do they say so? So what is the physics behind the non-existence of characteristic earthquakes in nature? Because they interact. So you have different fault systems interacting, and then you have, you can say Coulomb stress, you know, they act on each other. This changes all the time. You have other like fault systems, segments that interact with each other, and so actually you end up having clusters, right? And then long repose times, and then random again, another earthquake, and then not again. So actually, if you check the characteristic earthquake hypothesis, even with very long catalogs, you barely find them. They are not there, but you find them in some very specific situations, and generally they are volcanic. One is this one. It's really characteristic earthquake you have. Why? Because you have an isolated fault. It's just one fault, really. It's a ring fault. There are no other faults once it has well developed. And it is driven by a process that is relatively smooth. You know, you're draining something. The process is smooth, so stressing is really smooth. And then you have constant everything else, you know, and then you actually drive. It's like really like a pulling a mass on a friction. Is actually the solution of this problem is very similar, but just a very little variation to the solution of this mass being pulled. It's not really very different. There is only this additional term that due to compressibility actually resists the motion. Otherwise it's very similar. Okay, I'll tell you there is another instance I know, just to tell you, of characteristic earthquake related to magmatic system, and it is because sometimes there are actually two that I know. One is magmatic and the other one is not magmatic. The magmatic one is mid-ocean ridges. So basically you know that mid-ocean ridges are segmented, and you have this, and then you have this, and then you have this. You know, and here you have the spreading segment, and here you have a fault, transform fault, and here you have another spreading segment. So if you go to the Pacific, where the spreading rate is very high, it's like 16 centimeters a year, something like this, then you actually reach so we saw that in Ethiopia, at least for the upper segment, and in Iceland, we had kind of recurrence times of several hundred years. But there, the opening rate is like 2 centimeters a year, more or less, similar in both cases. Here we have 16 centimeters, so this accelerates. And also the dikes are very low viscosity because it's really mid-ocean ridge, even less viscosity, lower viscosity than in Iceland or Ethiopia. So actually what happens is that there are below fast spreading mid-ocean ridges, you have magma chambers that look like a flat lens, elongated lens. Below Earth there is probably a similar thing. So it's like a transition between continental and oceanic. You have these flatlands that were seen by seismic or gravity in the ocean floor. Okay, what are these lands doing? They feed actually, if I look in cross section, you have the mid-ocean ridge and then you have these lands, and they feed the vertical dikes that then basically they push aside, and you have all these dikes that create the ocean floor and create these ophiolites, you know, that we were discussing in the beginning, and the gabbro, which is the intrusive basalt. So basically you create dikes. These dikes are all here, and then you push, you know, and every 6 there is a segment, so some of these segments are monitored, and they see actually that you have a magnitude 6 every 5 years. Really, it's amazing. You really have it with a very, very, you know, within 1 year error, you know, so of course it's not really super precise like a clock, but you have these characteristic earthquakes. And again, the reason is that you have, so these faults, maybe they are segmented in 3-4 parts, and some have continuous swarms, some have these characteristic earthquakes, but the point is they are basically isolated faults. They don't interact with anything else, and you have a forcing that is very smooth because you have this regular ascent that then breaks them, and they are very smooth structure. We see that they are quite smooth because we see in the topography that there are really rectilinear, very rectilinear faults, planar faults, relatively smooth for being faults, and forced. So just to keep in mind what I need to have, and that I don't have to be surprised if my statistics is sometimes not good on the Richter, because not all, but it's rare. It's a rare thing. And the caldera collapse is one of those cases. Actually, there was a movie, if I find it, I didn't think about looking for it before. I'll try to find it. This one, yeah, maybe. It's a very cool one. You see, what you see now is the dike propagating from the caldera. Here, it's the caldera is activating. You see, there is no collapse yet. For now, the dike is still kind of starting, but not entirely, and then at some point you will see it will go. This is the dike, and then I'll stop it slightly, you see, and then here, so this is the dike from the magma chamber traveling this far. Here below the dike you have décollement, it's called, between the, so you have the flank of the island and you have the dike, and then there is, it's thought that the island is lying on top of the ocean floor, and therefore there are sediments here, so that all the flows basically are overlying sediments, and therefore this is kind of lubricated. So basically every time a dike pushes to the side, then you have a slip here, and you have earthquakes that occur on this. It's called décollement because it's like kind of unlocked. Yeah, it's like
horizontal. The fault
it's sub-horizontal. It's really quite almost horizontal.
Yeah.
So the focal mechanism of these earthquakes, it looks like really like, you know, like really horizontal.
Detachment.
It's a detachment, and the dikes push, and this detachment slips. So this is actually what is seen. I'll go back slightly. is what is seen by these earthquakes that occur here. You know, you see how many they come and then a big one? At some point, yeah, this one is a big one. It's really, oh, wow, this one. Okay, now look at the caldera. Okay, the caldera now, it's not really, I had seen an animation that was actually better for the caldera part. So this of course is very big. But the caldera part you would see boing, 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 like all the events that the caldera collapse was animation. There is not another one. Well, this was a magnitude, it was quite large, 6 point something, I think, that occurred, making the whole flank to slip due to the push of the dike. And also the caldera did collapse. Okay, so, yes. Okay, we were discussing, sorry, it's a bit chaotic. We were discussing the factors that lead to the change of these parameters. And actually, there is no really agreement yet. Everything can be. Probably the outflow rate is quite important because if we go back, here, so delta Z is decreasing, T is increasing. Okay, the only thing that can make, so we saw everything should be decreasing in the first equation to help delta Z decreasing. This means that actually the same thing should be decreasing in the last one. So why do I see T increasing? The only way to explain it is that actually alpha is decreasing very much. But we know that. We had the previous part of the class really on the outflow rate from magma chamber. And we know that except for the very initial part, where outflow rate is actually generally increasing, then it's decreasing. And this explains quite well why I have actually for the time interval first, it's actually decreasing and then increasing. It's probably because the outflow rate is doing the same. It's actually first increasing and then decreasing. And then it is dominating because it is, so while friction, volume also, but friction, magma compressibility and so on, they change by a fraction. They cannot change very, very much. Outflow rate really goes from 0 to a maximum to again 0. And then this is really a big effect on this equation. So here, you know, it goes from 0 to a maximum to 0. And therefore, the end result is that T goes from a maximum to low to a maximum again before it stops. So it's a very weird actually, but it is predicted by this model. No. It is very weird, but predicted by this model that the interval time increases until a maximum number and then stops entirely. So, and yeah. Questions on this caldera collapse? Okay, so I wanted to show you something else, which is this other paper. What is it? Not this one. Ah, no. Here. Okay, yes. So this is the lava flow measured from satellite data for the whole round eruption, for the Bardarbunga one. So it's a lava flow measurement from satellite, so there is no data, there are of course no data during the dike propagation because there was no lava flow. So it starts only at the time of eruption, and then it's plotted in logarithmic form. So you don't actually see very much the increasing phase because it is, but you have 2-3 points like here, 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 here. Here is the increasing phase, and then you see that it actually follows quite well a straight line. This tells you that it is really nearly exponential because it's plotted in logarithmically, and then you have a point where the flow, it's again like a straight line, but it's a different straight line. So apparently there is a different regime here. They explain it in terms of like a dike closure. This is an interpretation. I'm not sure this is the true reason, but you can see that this basically when this starts, the trend will actually more or less predict the end of the eruption, which occurs actually a month later. But if you, it's not really exactly, but it tells you more or less that the eruptions is going to end. So you have several trends and they are not yet understood. But this one is kind of understood. This one is this model that they do by this, they call it inelastic gravity model, by which the caldera collapses and then you have to consider only the weight of the magma column plus the piston to actually drive the lava flow. Of course, you have also to consider the different height of things, you know, to see how much actually when the eruption is going to stop. But this trend is not going to help you predicting the end of eruption. You see, at some point you will have a transition of regime, and only this trend helps you really get in the end of the eruption. So there is a time point when things change. Otherwise, you could go on forever. Basically, you could go on for a very long time. But at some point, something else. So actually, it would be very important to understand why this occurs. By the way, also for Kilauea, you had these earthquakes, the caldera collapse, you had the lava flow. The lava flow was really very, you know, intense. You remember the movies with this lava that was running like a river. And the people were saying, so when is it going to stop? And scientists were saying, well, with these trends, it can last really for many, many months. And then it stopped immediately, so like really sharply, it stopped like abruptly after just a few weeks. And people have not really understood why it stopped so abruptly. So this is still, probably it was something similar like here and it was not predicted. So what I want to tell you is that for volcanic eruptions, basic questions like where this is the eruption going to occur? So where is the vent going to open? When is it going to occur? And how much magma will erupt? We are still, you know, so it's like basic forecasts. Okay, earthquakes are even worse. We have absolutely no idea when, where, and how big. No idea, absolutely no ideas, and probably it's kind of impossible to. But for volcanoes, I don't think it's impossible. It's just that we are not there yet. We are not there yet. We cannot. So you saw the vent maps. Like, okay, I know where the previous eruptions have occurred. So I have a vague idea, but the data generally are not enough to go statistics, to go data driven, because I have only 80, 90 events at most in very big areas, and I have areas where I need to interpolate. I don't know really where the eruptions are going to occur, and so I need maybe probably more physics to actually predict this. Then when, also how long do I have? It's very important. I have activity in the magma chamber. I can even see that a dike is probably nucleating. How much time will this dike take to actually reach the surface? This may be relatively easy, although it's not that easy to predict or forecast for a lateral dike, because I can see from the very early time how long it takes, but you know, it has deceleration and then it takes again. You know, remember the Bardabunga dike, it did like this, then it did like this, then it did like this. So is it going to stop, erupt there? No, it actually went further, and in the end it erupted very far away. And these things are not understood. What are commanding them is like topography, is it really magma chamber, what are the processes commanding it? So the when and the where are very, very difficult to answer, and even more difficult is the mass flow rate, unless you have a very simple case. Like Bardabunga for mass flow rate is kind of simple here, you know, and then it becomes complicated again and we don't know why. But other eruptions, like for Kilauea, very difficult to answer. Mass, at the beginning was tiny, mass flow rate, then okay, it's predicted that it will increase because the fissures will become bigger and larger. And in that case also the composition changed, so probably it kind of reached a deeper chamber, and then everything started to flow really, really very fast. But then it was interrupted abruptly and nobody knew why. Nobody still knows why. So we can wait for some of the papers to come out and explain this. So here you see this, basically this is the discharge volume, so it's a kind of a cumulative, this was the rate, right? And this is the total volume, so it's cumulative, the cumulative of an exponential is still exponential, so it's an exponential, and here is this second type of, or other curve that deviates from this exponential, maybe also exponential, but with a different rate occurring here. And what they are showing here is that also the subsidence of the caldera floor was related to this, so basically that they were the same, and that the height of the column was commanding this outflow rate. This is what they wanted to show. And then I wanted to show another paper, which is this Aravena here, and there was another one by Piombo. What is it? No, this has nothing to do. Maybe here, or maybe I took it away actually. I think I took it away, whatever. So this Aravena et al. Is a paper that came out recently. It's called, it's like an example just to show you that things are starting to move. This is people in Pisa. In Pisa, actually, INGV in Pisa is one of the best centers to study these conduit flow models, plume expansion models, pyroclastic flow models. Is one of the one other is in definitely there is something in Japan. I'm sure there is. One is in the United States in Buffalo. There is a big center with volcanology where they do these models. There are many other centers with volcanology. I'm talking now about the flows. It's in Buffalo is one, and then there is Pisa, and then there are of course others, but these are among the most famous. And here they started to include, so here you see all these equations are this conservation of mass, momentum, energy, the mass of the crystal, dissolved gas, exsolved gas. These are all these equations that you see. They are written for the, you see this, the Bernoulli equation. One can recognize kind of some pieces of it, you know. See how complicated they get. These are for the different phases. When you see this X, it's generally the fraction of crystals and gas. This is the energy equation. One can kind of see what they are. And then what they put, here is the other equations. Here they put, basically this is a rough equation to consider the response of change in pressure due to a mass exit. So the one that I showed you is better. This one neglects, only keeps the elasticity of the rock and doesn't consider the part of the magma compressibility. But it's just to show that some people are starting to use it. And then, actually, the full equation is used by the Stanford group with the full part. It's already used the model that I showed you today with the big magma chamber. They used the full equation with the, that I showed you today for you. And then they solve all these by several algorithms. And then what they get is, I want to show the result, is actually here in the end. So effusion rates, and you can see, okay, it's not really what we showed, but you can see that these effusion rates, they first go up and then go down. And here they also use this conduit erosion. You know, and then for different parameters you have it more flat, for other parameters you get it more steep. And then there is another one here where you can see these effusion rates. The characteristic of this effusion rate is that it is kind of same time scale, the waxing and the waning. So probably they should change something to actually get what is actually measured. So now another question. If you have a model, if you get a model, let's say for a project, you get this model already coded. You don't have to do much. What you can change is the parameters of the model. You can change compressibility, you can change all the parameters that are input here, which are, you know, they are many. All these things that go in here. Initial radius for the chamber, you know, whatever. Many other parameters. But especially you can change magma compressibility, you can change, the initial radius, you can change the length of the conduit, you can change, you know, like geometry parameters plus magma compressibility. You have the entire numerical model. You have, you can see these previous results published in a paper that first attempted to use the model. What can you do? So your task is to compare basically this model with some observations. For example, the Bardarbunga one, like to say just an example. Let's discuss now, since we have like 5 minutes, what we can do with this code and the data. So you get the code and you get the data. What would you do to just, you know, on your first day and the second day and the second week? How would you behave with this kind of project? It's just a discussion, you know, to basically show you how an example of a potential project. So you can run the model, you can change the parameters. Okay, what can you do to, what would you do to see if you can get a fit to the model, a better fit to the model? Because this, you see, they don't really describe what the Bardarbunga dike was doing. You can check what parameters they put. I'm not even sure that they have a table. Maybe they have a table. Probably they don't. Should be better to have a table. Probably it's in the supplementary material, the whole list that they use.
Get more constraint and other parameter by the observation. It's just our modeling.
Okay, so this is a very first thing to do. So you go to the papers that were published on that particular eruption. For example, for the Bardarbunga dike, you know that the conduit was 40 kilometers long. So you can put that, and you can put, so what you know, you put in the parameters. 40 kilometers long, compressibility, you can kind of figure out from previous papers maybe, and other parameters you can kind of figure out. And if you do, it gets, let's say, it gets more similar, but not quite yet. Not quite the same. It gets better, but not the same. what will you do? It's just, you know, there is not one correct answer. It's just challenging you. For example, one thing that one could do,
By fixing the parameters and change one parameter to see which parameter dominated the process.
this is the one clever thing to do. You know, you fix some of them or most of them, and you only move one little by little, and you see how the curves are moving.
Can fit the observations.
Yeah, this is a good thing to do, definitely. It's one of the first things to try, to just change one at a time. And then what can you do? Maybe one thing that one can try is to set up a statistical method like we saw in the morning, by which you change them randomly within ranges that you think are reasonable, and then you get a set of curves and you look at the most similar ones, at the misfit between your measure curve and the result curve. You find a way to measure the misfit, maybe the total length and the position of the maximum. You may find the different measures of how the curves are similar, their total duration, the presence of the where the maximum is, the slopes, I don't know, or the, you know, you need to figure out a way, and then you can figure out what parameters are best, and then maybe they actually are unreasonable. And then what do? You go and you need to discuss. So then either you go back to the equations, or you go to, yes, so one other thing is, okay, like here I told you, one equation is actually not at the standard, but you need to have read other papers that show a different equation. And then you know, okay.
We
Then
compare the result to the different result with the
Yeah,
other type of
exactly. And then you change it just one maybe. The others are established, and then there is a new one that they put. So this is generally the trickiest point, you know. Sometimes you have really to go back, because sometimes the assumptions are wrong and you need really to go back, and people have used the same wrong assumptions because nobody questioned it, and then you have to go back. But sometimes it's the most recent that they use is the, you know, more fragile, so you attack that first, and only if you need, you go really back, and then you find a way. Okay, so tomorrow we will do stress interaction, like triggering of earthquakes and volcanoes, and another thing that I cannot remember right now. And this is it. So, yeah, see you tomorrow.